those.
Okay. So along the way, if you do have a question, you could unmute yourself. I'm setting the mute button right now, but just find a good place to pause and ask your question. Share our screen. So the PowerPoint is posted, something you could download and print out, or depending on what works for you, or just follow along. It's important that we define it first, acid and bases. It turns out that chemistry, they always kind of make things complicated. There are, in fact, three definitions of or three ways that you can define an acid or a base. But the one that we're going to be focusing on is, in fact, the third one I didn't even indicate here. It's called the Lewis acid and Lewis base. But the one that we're focusing on is this middle one, Bronsted-Lowry definition. Part of the reason why Arrhenius definition, the one on the first column here, is not the best way of defining it. It works well for the definition of an acid, but it doesn't work for the definition of the base, mostly because they define bases as compounds with an OH, known as hydroxide, which is almost entirely true, but there are exceptions. There are some bases that they don't have this, but they still can act as a base. Because of that, if there's an exception, it's a bad definition. Bronsted-Lowry is a more general way of defining an acid and base, and there's no exception to it. So that's the one we want to focus on. An acid is defined as something that's able to donate or produce an H+. H+ is read as a proton, or sometimes read as proton. Most of the time, students just call it H+. But the official name is called hydronium ion. That's the name of H+. So an acid is something that has an H+, and they're able to give that away to something else. Whoever is picking that up, that H+, is known as the base. So in this scenario, in this reaction on the right, this is just a generic reaction. HA corresponds to our acid. So the H is the proton that could be donated. And then B corresponds to our base. Notice what happens on the right side. The base picked up that H, the hydronium, thus creating, it now has a different role because it's now holding on to that H+. Its new name is now called the conjugate acid. It's the new acid after the reaction that occurred. A, on the other hand, lost that H+, so it's now considered the conjugate base. It's the new base after the reaction have occurred. So Bronsted-Lowry definition is the one that we use, especially for year one. Year two chem, there's a third one that you'll consider. It's called Lewis acid and base, but that's something separate later on. A few other things to note about acid and bases. We're pretty familiar with them because we use them quite often. We consume them. We have some of it in our system. For example, we eat a lot of things that is acidic, and don't they have a certain sourness to them? So if you think about lemon, orange, coffee, the flavor that they have tends to kind of fall in this category because acids tend to be sour. The more powerful acids tend to be corrosive, and they can be caustic as well. So they could break down metals. They could, sometimes they use it to remove rust, but those are the really strong acids. And then caustic could be like something that's harmful for us, right? When it touches your skin. Bases have a certain kind of property to them where the ones that we consume, they tend to have this chalky or bitterness to their flavor. With regards to the ones we use in our household, they tend to be used for cleaning. So like cleaning detergents or soap that you have in your bathroom has a component that's basic. Sometimes when they say something is basic, they also describe it as something is alkaline. So you might hear me say it describing things that are bases as alkaline substances. The video I showed earlier, and what I'll do is I'll post the link to that YouTube clip on our Google Classroom. I was showing the two different ways we could qualitatively test for acid and bases, and that is the litmus test and then the universal indicator. So the litmus test, what it does is it verifies if the blue litmus paper stays blue, it must be a base. But if it turns red, then we're dealing with an acid. And the reverse is true for the red paper as well. If the red paper stays red, it's an acid. If it turns blue, then we're dealing with a base. So that's kind of a way for us to check that. pH, or the acidity and how basic something is, or the alkalinity, falls in the range of 1 through 14. And on this particular slide, what it's showing is that we have all these different materials in our house that we're surrounded with that we use pretty regularly that are considered acids and bases. And they fall in different ranges. Inside our body, we have gastric juices that helps us with digestion, and they are pretty acidic. In fact, for those of you who have experienced it before, maybe have like a regular issue with it, this acid reflux, where acid's kind of like getting into your respiratory tract. So it has this burning sensation, right? Because the acid we have in our stomach is so strong. It's one of our stronger acids. Things that are also pretty strong are lemon juice, depending on the amount and the concentration, has roughly a pH of 2, fairly strong. And as you go further down the list of things here, we have coffee and soda are also very strong, and your dentist will always kind of remind you to make sure to not consume as much of it because it degrades the enamel. So what that process is, what's happening there is actually an acid-base reaction. So the acid is chipping away on the enamel, the outside layer of your teeth. So something you want to avoid. On the right side, we have our bases. So these are the things that you can see many are household cleaning materials. Like if you're having an acid reflux or heartburn, then you might take, like, let's say milk of magnesia, or take like Tums, something that has baking soda in it to neutralize. So when acid and base combine, it's called the neutralization reaction. The one reason why I wanted to show this slide is I wanted you to see that every time you're going from one pH level to another pH level, the change in concentration of H plus is actually a 10-fold change. So let me just draw something here. For example, if you were to compare, let's say a question says, how much more concentrated is stomach acid compared to lemon juice, meaning from 2 to 1. That's what we're trying to compare. Notice that the concentration changes 10-fold. It's a 10-fold change. So every number that you're going, that you're changing to, so if I'm going from a higher pH to a lower pH, lower pH means more acidic, then it's going to be 10 times more concentrated. But if I reverse the process, what if we're going from, let's say, I'm comparing soda to tomatoes, and then there's how, if I'm going from 3 to 4, what's happening to the concentration of H plus? Then, so meaning we're going from a lower number to a lower pH to a higher pH. Then technically what happened is we're now 1/10 of the original concentration. So the key here is that the higher the lower the pH number, the lower the pH number, the more concentrated it is, the greater the concentration. So kind of notice what I have written here, because on the next slide we're going to use that information to answer some practice problems. Clear this up, and let's give this a try. pH scale. So in the next slide, we have the same range here, but now we have the colors. So in the video I was showing you earlier, in the demo I was showing you earlier, I did an experiment using our universal indicator. And one of the containers had water in it. So that particular container falls within this range, perhaps between 6 and 7. It might not be perfectly at 7 because it was not pure water. There were other things in there. So and then the other container had hydrochloric acid, which is one of the stronger acids that we use in our class. So with that, it falls in this range. Question 1 says, which end has the greatest H plus concentration? This region, meaning the lower the pH, the greater the concentration of H plus, the more acidic it is. So those three are connected. Greater concentration, lower pH, it's more acidic. So this is the region where it's more acidic. Then obviously the opposite is true on the other side. The far end would be the least acidic, but if you kind of like flip the coin, least acidic is another way of saying it's the most basic, so most alkaline. So just keep in mind that it's a full range from 1 to 14, and the neutral is right at the middle, which is a 7. Question 2 says, if we're going from pH 4 to 3, so we're going from here to there, how much did H plus change? So we're going from less to more acidic, which means, and I mentioned earlier, every time you go from one pH to another, it's a 10-fold difference. Since we're going to something that's more acidic, isn't this 10 times more concentrated? So from 4 to 3, it's 10 times more concentration of H plus. Now, question 3 says, what if we're going from 6 to 8? So isn't that a 2-step process? Meaning we have to go from 6 to 7 and then 7 to 8. This time around, we're going from something acidic to something less acidic, which means it's not 10-fold, like it's not a 10 times every time, it's actually 1/10 every single time you're going from 6, 7, and then 7 to 8. So the calculation for this would look something like this: 1/10 times 1/10 gives us 1 over 100. So to answer question number 3, if we are going from 6 to 8, the H plus concentration is now 1 over 100 compared to the original. It's you can call it, it's less concentrated, or usually we say it's more diluted. So it's not as concentrated compared to a pH of 6. So in a way, it's like a concept in math type of idea, but in terms of the math, it's really just a matter of, are we multiplying by 10, going to more acidic, or are we, if we're going to less acidic, then it's always like 1/10 of a change, and we're multiplying that however many times you move down your pH scale there. All right, so let me clear that. And again, if you have a question, unmute, ask your question, or there's a raise hand function on your end, so you can do that as well. I'm gonna keep going. So the test that I did was using a universal indicator, and there are other indicators there. If we were able to do a lab, we would have done one where we would test phenolphthalein, the first one on this list here, and we would have done a titration. So I just needed to at least include and mention that there are many ways that you can test for acid and bases using different indicators. The one I used for today's demo was a universal indicator. And each one that's on this list specializes on a particular range of pH. So they kind of give you an idea. For example, it looks like if you're using bromothymol blue, then you must be doing some sort of experiment that falls within the range of 6 to 8. That's kind of its prime range that it works well. All right, so those are pH indicators. Those of you who take AP Chem, you will for sure use this. I think even AP Bio would do some sort of experiment that deals with pH indicators. Now, with regards to the math of this topic, so pH is the measure of how acidic something is. For alkaline, alkaline again is, it's basic, meaning it's not acidic, or the opposite of it. And it's all entirely based on the amount of this, the concentration of H plus. Keep in mind again, it could take different names. H plus and H3O is the same exact thing. It's basically an H plus that's attached or interacting with water. So that's why it's called, or it's set up like this, H3O plus. The name of this is hydronium. So depending on the question, they might say, what if you have a concentration of hydronium of 5 times 10 to the negative 3? And you're like, what's hydronium? It's all the same thing. H plus, H3O, hydronium, proton, they're referring to the same thing. As I mentioned earlier, pH 7, which falls in the middle range, is the neutral pH. And now the thing is, calculating the pH is based on this first formula, but there are other formulas that's kind of related to it. So I've included all three on this one slide. And we're going to use, later in the 2 slides from now, we'll use all three on the practice problem. You'll notice that we're dealing with logarithms. So this is the time of the year where Algebra 2 comes into play. Well, one thing is, unlike in your math class where you're probably like learning the rules with logs and natural logs and what to do with them, for us it's calculator based, right? So it's a formula-based calculation that you put in your calculator. On my calculator, there's a log key right there. And the inverse of this is 10 to the x, which is something that we'll use later on. Most of you have a graphing calculator, so it will also have a key specific to logs. When dealing with logs, the idea is that a minor change is actually a tenfold change. So it's something that it might seem like you're just changing by a few decimal, but in a way, the effect of it is tenfold. So you really want to be as precise as possible when reporting your answer for logarithms. So because of that, because of this, the concept that a small change actually is a adverse, like a big change to the number, we have to kind of follow a specific rule with pH. It turns out, I mean, I'll read this, but the example clarifies the statement. The number of decimal places for a log must be equal to the number of sig figs in your concentration. So what I mean by this, let's use an example. What if your concentration of hydronium or H plus is 1.0 times 10 to the negative 5? Remember way back in the earlier part of the year, when looking at this number, we don't really factor this as your sig figs. The sig figs is the base number. So we have 2 sig figs on this given. Now let's plug it in on our calculator. So plugging the whole thing, negative, don't forget that, it makes a big difference. Negative log of that, of our given, we end up with 5.00, and there are perhaps other numbers out after that. It's gonna be like a bunch of zeros. How do you decide when to stop, like what to report it as? It turns out that based on your number of sig figs, so if you have 2 sig figs, then we need to match that number. 2 sig figs, 2 decimal places. So be careful, because it's not, the answer is not like 2 sig figs. It's saying if we have 2 sig figs, then we need to report it with 2 up through the hundreds place. So 5.00. We'll try a practice problem that kind of is related to this. So let's start right here. Using the same 3 formulas, I should probably note, this is the main one, pH is negative log of H plus. But if the question is asking about how basic something is, then another way, or another formula that's very much related, is a measure of POH, the measure of hydroxide. So you'll notice it's the same setup, negative log, but instead of H plus, we're dealing with OH minus. And then it turns out adding the 2 together adds up to 14, which is the full range of acid and bases. So with that, let's answer the first one. Let me draw this. So they're asking, what is the pH if we are given 2.3 times 10 to the negative 4? So set up, the pH is equal to negative log of the given, and our given is 2. Right, is 10 to the negative 4. All right. Plugging it in my calculator. So don't forget the negative, because again, it makes a difference. Negative log of, and then I highly suggest to use parentheses again. So depending on your calculator, maybe the graphing calculators can figure it out without any kind of issue on your answer, but it's crucial for scientific calculators to have that sign inside the parentheses. So it gives me a pretty long number. So you guys can kind of see my answer there. Now, based on the sig figs rules I was just talking about in the previous slide, isn't this 2 sig figs? Our given is 2 sig figs. So I need to report my decimal places to decimal places as well. So looking at my answer here, 3.6385, I need to stop at the second decimal place, but I have to follow the rules of rounding, which forces me to report it as 3.64. So the pH will be 3.64. The second question says, what is the pOH? So we've used the first equation. We can use the third equation. Since our pH is 3.64, and based on the third equation, adding that to pOH adds up to 14, which means, isn't it just a subtraction? 14 minus 3.64 gives us pOH of 10.86. All right, so now we have our pOH. Our third, so this is A, B. For part C, they said, great that you have your pOH, but now can you figure out the concentration of OH minus, that hydroxide, which tells us we got to use the last equation here. 10.36 is the pOH. And then it's a negative log of OH minus. So now the missing, or what's missing, is on the right side. We have our pOH from the previous step. We got to get rid of the negative, and we got to get rid of this log. So the negative is easy. So to get rid of that, you could say, well, I can divide both sides by -1. Just by doing so, then I can get rid of that negative on that side, and what will happen is this will now become negative. So just trying to get rid of negative on the right side. But how do we get rid of that log? So the inverse of that log is over here to your calculator, and based from what you learned in your algebra 2, it would be a 10 to the x, which would kind of get rid of that logarithm for it. So essentially 10 raised to the power of log cancels this whole thing. But if you do that on that side, you have to do the same thing on this side. So this means, and this is really what we need to plug in our calculator. So on mine, if let me see if I can point at it, you'll notice here it says log, but the inverse of it is 10 to the x. So all I need to do is shift log, and then my negative sign. Do not forget that negative, 10.36. If you do, you'll see your answer is completely different. So it looks like the final answer, the concentration of OH, is 4.37 times 10 to the -11. Capitalize M for clarity. I guess here's the final answer for OH. Here is our pOH, and this is our pH. So those are the three answers for practice problems A, B, and C. And these are like the typical type of question you'll get for year 1 chemistry. All right, I'm gonna pause for questions. In fact, let's pause our recording.